Download this code from codegive.com, link in the description below. Demystifying Modern Windows Rootkits, a detailed tutorial with code examples. This tutorial delves into the world of Windows rootkits, focusing on modern techniques and providing code examples to illustrate key concepts. We'll explore the different types of rootkits, their functionalities, detection methods, and how to build a basic, and ethical, proof of concept. Disclaimer *: This information is provided for educational purposes only. Creating and deploying rootkits is illegal and unethical. This tutorial aims to help you understand how rootkits work so you can better defend against them. I am not responsible for any misuse of this knowledge. Introduction to rootkits. A rootkit is a type of malicious software designed to hide its existence and the existence of other malware from the operating system and its users. They provide persistent and stealthy access to a compromised system, allowing attackers to perform malicious activities without being detected. Why are rootkits so dangerous? Persistence. They can survive reboots and system updates. Stealth. They conceal themselves and other malicious components. Control. They grant attackers privileged access and control over the system. 2. Types of Windows rootkits. Rootkits are categorized based on where they operate within the system's architecture. Here's a breakdown. User mode rootkits. These operate at the application level, Ring 3. They are easier to develop but also easier to detect. Function hooking. Intercepting and modifying calls to system APIs. Instead of directly calling a legitimate API, example read file, the call is redirected to the rootkit's code, which can manipulate the data returned or perform other malicious actions. Process hiding. Preventing processes from appearing in task managers and process listings. File hiding. Making files and directories invisible. Registry hiding. Concealing registry entries used for persistence or storing configuration data. Kernel mode rootkits. These operate at the kernel level, Ring 0, giving them the highest level of privilege and control over the system. They are more difficult to develop and debug but are also much harder to detect. Direct kernel object manipulation, DKOM, directly modifying kernel data structures to hide processes, files, or other objects. System call table hooking, SSDT hooking, modifying the system service dispatch table, SSDT, which maps system call numbers to the corresponding kernel functions. This allows the rootkit to intercept and modify system calls. Interrupt descriptor table, IDT, hooking. Intercepting hardware interrupts to gain control of the system. Driver-based rootkits. Installing malicious device drivers to execute code in kernel mode. Hardware-based rootkits. These are rare and complex, residing in the firmware or hardware components of the system, example BIOS, hard drive controller. They are very difficult to detect and remove. Bootkits. These infect the master boot record, MBR, or the UEFI firmware, allowing them to execute before the operating system loads. This makes them extremely difficult to remove. Virtual machine rootkits, hypervisor rootkits. These operate below the operating system level, in a hypervisor environment. They can control the operating system running inside the virtual machine. 3. Core concepts and techniques. Let's examine some essential techniques used in rootkit development, along with code examples. We will focus on user mode and kernel mode techniques. User mode. Function hooking. Function hooking involves intercepting calls to functions in DLLs, often system APIs, like those in kernel 32.dll, user 32.dll, and ntdll.dll. This allows the rootkit to modify the behavior of applications and the operating system. Techniques for user mode hooking ****IAT, import address table, hooking * modifying the IAT of a process to point to the rootkit's functions instead of the original DLL functions. This redirects calls to the hooked function. Inline hooking, DDIRs directly overriding the beginning of the function in memory with a jump instruction that points to the rootkit's function. Example, IAT hooking, C++. Explanation ***. One hooked message box a **r hook function. It displays a message indicating it's been called, modifies the original text and caption, and then calls the original message box to display the modified message box. 2 hook function ***. This function performs the IAT hooking. It iterates through the import address table of the specified module, usually the current executable, and finds the entry for the function we want to hook, example message box. 3 IAT modification ***. Once found, the code modifies the IAT entry to point to our hooked message box a function. Crucially, it saves the original function address for later use. 4 virtual protect ***. The virtual protect function is used to change the memory protection attributes of the IAT, making it writable. After the hook is installed, the protection is restored to its original state. 5 Calling the original function * within hooked message box a, we retrieve the original message box of function pointer and call it. This ensures that the message box is still displayed, but with our modifications. Important notes ***. Error handling ***. The code includes basic error handling, but real-world rootkits often employ more sophisticated error handling and obfuscation techniques. Module selection ***. The example hooks message box within the current executable. Rootkits often target functions in system DLLs. Unhooking ***. A complete implementation should include a function to unhook the function and restore the original IAT entry. Anti-hooking techniques ***. Modern software often employs anti-hooking techniques to prevent IAT modification. These techniques can include checksum verification, memory protection, and code integrity checks. Kernel mode rootkit techniques. Kernel mode rootkits operate at the highest privilege level, ring 0, giving them the most power and stealth. Key techniques ***. 1. Direct kernel object manipulation, DKOM. DKOM involves directly modifying kernel data structures to hide processes, files, or other objects from the operating system. This is a powerful technique but requires a deep understanding of the Windows kernel. 2. System call table, SSDT, hooking ***. The SSDT is a table within the kernel that maps system call numbers to the corresponding kernel functions. By modifying the SSDT, a rootkit can intercept and modify system calls. Example, SSDT hooking, C++. This is a simplified example illustrating the concept. It requires a kernel mode driver project. You need to build this in a WDK, Windows Driver Kit, environment. Explanation ***. 1K service descriptor table ***. This global variable, exported by entiskernel.exe, points to the SSDT. 2 Original ZW create thread X and hooked ZW create thread X * pointers to store the original ZW create thread X function and our hook function, respectively. ZW create thread X is a kernel function used to create new threads. 3 Hooked ZW create thread X * our hook function. It prints a debug message and then calls the original ZW create thread X function. You would insert your malicious logic here, example modify thread creation parameters, log thread creation events. 4. Disable write protection and enable write protection *. The CR0 register controls various processor settings, including write protection. To modify the SSDT, we must disable write protection by clearing the WP bit in the CR0 register. Carefully handle this. Improper use can lead to system instability. We re-enable write protection after the modification. 5. Driver entry *. The driver's entry point. It obtains the original ZW create thread X address from the SSDT, hooks the function by replacing the SSDT entry with the address of hooked ZW create thread X, and disables write protection during the modification. 6. Driver unload *. The driver's unload routine. It restores the original SSDT entry and re-enables write protection. It's crucial to restore the original SSDT when unloading the driver to avoid system instability. 7. Correct pointer assignment *. The lines k service descriptor table - service table base equals are crucial. The service table base member of the k service descriptor table is the base address of the array of system service routines. You're directly overwriting an entry in that array to point to your hook function. Important considerations ***. Kernel mode risks ***. Kernel mode development is inherently risky. Bugs can lead to system crashes, BSODs. Thorough testing is essential. Security features ***. Modern Windows versions have security features like patch guard, kernel patch protection, that actively prevent modifications to the kernel. Bypassing these protections is complex and requires advanced techniques. This example will not work on systems with patch guard enabled without additional steps to bypass the protection. Code signing **. Kernel mode drivers must be digitally signed with a valid certificate to be loaded on 64-bit versions of Windows with driver signature enforcement enabled. C. Process hiding. Rootkits often hide processes to conceal their malicious activity. User mode ***. Hooking create tool help 32 snapshot, process 32 first, process 32 next ***. These APIs are used to enumerate processes. The rootkit can filter the results to exclude the hidden process. Hooking anti-query system information ***. This native API is used by many task managers and system utilities to retrieve process information. The rootkit can modify the returned information to hide the process. Kernel mode ***. DKOM, direct kernel object manipulation. The rootkit can remove the target process from the active process links list in the process's process structure, effectively hiding it from process enumeration. Example, DKOM process hiding, kernel mode, simplified. Explanation ***. 1 PS lookup process by process ID ***. This kernel function retrieves a pointer to the process structure of a process given its PID. 2 Remove entry list ***. This function removes the process structure from the active process links list. This list is used by task managers and other utilities to enumerate processes. By removing the process from this list, it becomes hidden. 3 OBDereference object ***. This function decrements the reference count of the process object. It's essential to call this after obtaining a process object with PS lookup process by process ID to avoid memory leaks. Important considerations process structure the exact layout of the process structure can change between Windows versions. The provided structure is a simplified representation. You need to obtain the correct structure definition for the target Windows version. Synchronization kernel mode operations must be properly synchronized to avoid race conditions and data corruption. This example lacks proper synchronization and is suitable only for demonstration purposes. Reliability DKOM is a delicate technique. Errors can lead to system instability. Alternative hiding techniques. More sophisticated techniques involve manipulating other kernel data structures or using callback routines to filter process information. 4. Rootkit detection and removal. Detecting rootkits is challenging due to their stealthy nature. Here are some common detection methods. Signature-based scanning. Traditional antivirus software uses signatures to identify known rootkits. However, rootkits can easily evade signature-based detection by using polymorphism and obfuscation. Behavioral analysis. Monitoring system activity for suspicious behavior, such as unexpected API calls, kernel mode code injection, or modifications to system files. Integrity checking. Verifying the integrity of system files and kernel data structures to detect unauthorized modifications. Rootkit scanners. Specialized tools designed to detect rootkits by using a combination of techniques, including signature-based scanning, behavioral analysis, and integrity checking. Examples include GMER a free rootkit scanner. Rootkit Buster from Trend Micro. Sophos Anti-Rootkit from Sophos. Offline scanning. Booting from a trusted environment, example a rescue disk or live CD, and scanning the system for rootkits. This can bypass rootkits that are active during the normal boot process. Memory dump analysis. Analyzing a memory dump of the system to identify rootkit code and data structures. This is an advanced technique that requires specialized tools and expertise. Rootkit removal. Removing rootkits can be difficult and may require specialized tools and expertise. Here are some common removal methods. Antivirus software. Many antivirus programs have rootkit removal capabilities. Rootkit removal tools. Specialized tools designed to remove specific rootkits. Manual removal. For advanced users, manual removal may be possible by identifying and removing the rootkits files, registry entries, and kernel mode components. This is a risky process and should only be attempted by experienced users. System restore. Restoring the system to a previous state before the rootkit infection. Reinstallation. In some cases, the only reliable way to remove a rootkit is to reinstall the operating system. Advanced rootkit techniques. Beyond the basics, advanced rootkits employ more sophisticated techniques to evade detection and maintain persistence. Virtualization-based security, VBS, evasion. VBS creates a secure enclave within the operating system, isolating critical components from the rest of the system. Rootkits may attempt to bypass VBS to gain access to these protected components. Direct hardware access. Some rootkits may attempt to bypass the operating system and directly access hardware components, such as the hard drive or network adapter. This allows them to operate completely outside the control of the operating system. Firmware attacks. Infecting the firmware of system components, example BIOS, UEFI, allows the rootkit to persist across operating system reinstallations and even hardware replacements. Anti-forensic techniques. Rootkits may employ anti-forensic techniques to erase traces of their activity and make it more difficult to investigate the infection. This can include wiping logs, deleting files, and overwriting memory. Kernel obfuscation. Employing sophisticated code obfuscation and encryption techniques to make it difficult for security tools to analyze the rootkit's code and behavior. 6. Ethical considerations. It is crucial to emphasize the ethical implications of rootkit research and development. This knowledge should only be used for defensive purposes. Ethical hacking. Use your knowledge to penetration test systems with permission and identify vulnerabilities. Security research. Contribute to the security community by researching new rootkit techniques and developing countermeasures. Education. Educate others about the risks of rootkits and how to protect themselves. Never use your knowledge to create or deploy malicious rootkits. 7. Conclusion. This tutorial provided a detailed overview of Windows rootkits, covering their types, techniques, detection methods, and removal strategies. The code examples illustrated key concepts, but it's important to remember that real-world rootkits are often far more complex and sophisticated. By understanding how rootkits work, you can be better prepared to defend against them and protect your systems from attack. Continue your learning journey by exploring more advanced techniques, researching the latest security threats, and staying up to date on the ever-evolving landscape of malware. Remember always to prioritize ethical and legal use of this knowledge.